So you can see the screen, right?
Yes, sir.
Okay. So that was our common emitter, common base cascode amplifier. Okay, so first I write the different features of this one that we obtained for in our last class. Ri was just R phi 1, and the output resistance R naught or small R naught times 1 plus Gm, that was Gm1 or Gm2 R phi 2. Was it Gm1 or should be Gm1? No? Gm1 R phi 2. Yeah. Oh, Gm2 R phi 2, sorry. Gm2 R phi 2, and then that we simplified as, okay, so R naught 2 or R naught 1, R naught 2, R naught 2. So that we can simplify as R naught 1 plus beta, right? Gm R phi is beta. And the voltage gain V naught by Vi, that was minus Gm. It was Gm1, and then R. And then current gain was I naught by II, which was minus alpha 2 beta 1, alpha 2 beta 1, and that can be approximated to minus beta, right? Okay, so these are the apply the input resistance, the gain, the voltage gain, current gain, similar as those of the common emitter. The gain here for common emitter, we have the R naught, small R naught, we don't have it here. This is the main difference here, that the output resistance is very high, right? So that is the main difference. So now today we'll see a modification of this circuit. The modification is that so basically we replace the transistor with a MOSFET here, or Q2. So this one now this is a common emitter, and what do we call it? This is our this will be common emitter, common gate. Right? The gate is grounded. The common emitter, common gate cascade amplifier, also known as BiCMOS. BiCMOS cascade amplifier. So now, so what difference it would make then? We start with the input resistance. We see that the input resistance remains same. There will be no difference, R by 1. The output resistance. So what we can write for the output resistance? Any idea? Hello guys.
Yes, sir.
What will be the output resistance? No idea.
Sir.
From the output side, it looks like this, right? So this is our Q2. And then down here, instead of Q1, you can just draw a small r not 1, right? And you're looking from here, the output resistance. Right. It's like a common emitter with emitter resistance. This is common source with source resistance. Right? So similar formulas also apply, right, that we used for the common emitter with emitter resistance. So R naught, the output resistance will be here the okay, let's change the color. First, the small R naught, that's R naught 2, and then you will have 1 plus GM for Q2, and then you have the resistance in the here, in this case, source R01 in parallel with. Now, in parallel with what?
Sir, 1 by GM.
1 by GM for common emitter case, right? Not common, for, yeah, for transistors. What did you use?
Sir,
What
alpha.
resistance? And alpha, what's the resistance alpha? Looking from which side?
Sir, in MOSFET side, sir, it is open.
You're looking from the base side, so in this case, the resistance is looking from the base side, right? And if you look from the gate side, resistance is infinite
Yes.
because it is open, as I said. So what you will have instead of this, you'll have R pi, you have infinite resistance, right? So R naught in parallel with the infinite resistance that you see from the gate side, right? Looking into the gate. So that will be our expression for the output resistance. And then what does it will simplify to? R naught in parallel with this infinite resistance. Hmm.
Sir, R not 1.
Hmm. So GM2 is small R01. So R01 is high, but if you compare with the infinite resistance, this is nothing, right? This is very small. So the parallel combination will be the small one. And so that will be our output resistance. Now, if you compare this output resistance with the resistance that we have got here, and in this case, R naught times 1 plus beta, and beta was the GM R pi. And in this case, we have GM R01. Now, which one will be higher in this case?
Sir, the new one.
This one will be even higher because instead of R pi, you have R0, right? The output resistance. So that is usually much larger than R pi. So what we can say that here for the output resistance for BiCMOS cascade amplifier is much larger than R0 of that BJT, right? BiCMOS amplifier, BJT cascade amplifier. So we can have even higher output resistance. We can further increase the output resistance by using this BiCMOS MOSFET amplifier, cascade amplifier. Is that clear, guys?
Yes, sir.
Yeah. And the other parameters remain same, like if you think about the voltage gain, it is the same because what happens here, the same current flows, the way we deduced in our last class. This is our I. This is our IC1, right? And then this is here ID, right? And that is equal to minus I naught, or I naught is minus I. And ID, this is the same as the IC1, right? Same current, because this current here is 0. So that's the only difference. For BJT, this is just IC by alpha, and this is just exactly the same. So that is very easy to deduce the voltage gain in this case. So you just write that P naught is I naught RL, and that is minus IDRL, and that is minus IC1RL, and that is minus GM VBE, right? GM1 VB on RL, and VB is our VR, right? So what do you get? That the voltage gain V naught by VR, you get minus GM RL, right? GM1 RL. So it's the same, exactly same. There's no difference, though there is a difference of the factor alpha, right? But that is very close to 1. And the current gain. Current gain also, here you have alpha, but that alpha will not have alpha because the same current flowing. So it will just minus beta. So the other parameters, input resistance, the voltage gain, current gain, are almost same, and just the difference in the output resistance. So we can further enhance the output resistance by replacing the BJT with the MOSFET. Is that clear, guys? Any question?
No, sir.
So one interesting aspect is that it is possible to even further increase the resistance, the output resistance. We have the input transistor Q1, and then you have this MOSFET, that is Q2, and then you have this, another MOSFET here. And that is Q3. So it is possible to have kind of like this. So then what will be the output resistance? You see that in this case, there is no change in the current because the same current will flow, right? Whatever I see on the same current is flowing because the current here is 0. So the voltage gain remains same, current gain remains same, the input resistance remains same. Everything remains same, but only we can have a change in the output resistance. How it will change? Now this circuit you can draw like this. What will be our equivalent circuit here? From the output side, no, not this one. Okay, so from the output side, if you look from the output side, you see you have the Q3. Then what is connected here, that we can replace by an equivalent output resistance. Let's call it R naught prime, right? So then the equivalent circuit here you can draw like this. You have the you have R naught prime, and then you have this. That is your Q3. So what is your the R naught, right? So in this case, so what do we write for R naught?
So R0 3
R naught 3 times
1 plus GM3
1 plus GM3. Then we have
R0 prime parallel infinite.
infinite, right? So obviously R naught prime will be much smaller than this infinity resistance. So this you can approximate to R naught 2 and 1 plus R naught 3, sorry, R naught 3, GM3, R naught prime. So now what is R naught prime?
Sir, the previous output resistance.
Right. So this is our R naught prime, right? So looking from the output side of Q2, right? So that is the same here. So that is our basically the R naught prime, right? This part is our R naught prime. So already this is we said is higher, much higher than what we have for the BJT cascode, right? Now here what we have that now GM is being multiplied by this much higher output resistance R naught prime. So now overall, so the resistance that we get, right, will be even higher. Right? So that is our the R naught 2 and 1 plus TM2 R naught 1, right? So what we have now, the two stage, this cascade amplifier, the output resistance will be even higher, right, than that of our previous case. So this is how you can increase, right? So the output resistance to the extent that you can call almost infinite, right, for practical purposes. Any question, guys?
No, sir. Sir, but why we are increasing this output resistance so much?
Yeah, that's a good question. What do you think? If you think about the common collector, we try to increase the input resistance, right? The focus was the input resistance and voltage buffer should have infinite input resistance. Right? So we try to increase the input resistance by cascading the two common collectors, then replacing one with the MOSFET, and we achieved, ideally infinite input resistance. But for here in this case, cascode, we're trying to, the feature of the cascode is the high output resistance. And we're trying to increase it even to even higher level. And why are we doing that? Because this, in the cascode, we can use this as like something, current buffer. We can, the common base works like current buffer, it has a high output resistance. And you see that the same current will flow from the, and this same current goes to the output, right, to the load, right? And if it's like a current buffer, and ideal current buffer should have infinite input resistance, right? If you're talking about ideal current buffer, right? So it should have, not should be infinite. Ideal current buffer, like ideal current source, right? At the output side is working like a current source, and ideal current source should have infinite output resistance. There will be no output. This is usually current source we show like this, right? the output. For ideal case, this should be infinite, so that no current will flow into the this output resistor. All the current will go into the whatever load is connected here. And current buffer, so this is current source will write like this AI, and in the case of current buffer, this is 1, right? So that is how it will be, right? When you are talking about the current source or current buffer or current amplifier, the gain is 1. The common base current gain is 1. So it works like a current buffer. And the higher the output is, the better it will be as a current buffer, because more and more current will flow to the load, less will be the output resistance. So if you can make this infinite, right? So the current here is 0. Okay. And all of the current, will be passed to the load. Is that clear?
Yes, sir.
Okay, so next, what we discuss. So that is the end of our discussion on the multi-stage amplifier. We have discussed the cascade and cascade configurations for the multi-stage amplifier. And the two configurations, they have two different features to, yeah, I mean, they have also different applications. Now we'll discuss another next topic is our differential amplifier.
Sir, so mid syllabus is up to this point, right?
Yeah. Oh, what happened? Yeah. Like this. So this is a circuit that we call the differential amplifier, and this looks maybe complicated, but this is nothing but two common emitter amplifiers. They're tied at the emitter, right? This is one common emitter amplifier. Common emitter is grounded in this case. It is connected to the emitter of another common emitter amplifier, right? And there are two inputs, and we can take output from either of the collectors, we denote as VC1 or VC2, or we can take output differentially between these two collectors, which is denoted as VOD. VOD is the difference between VC2 and VC1, right? So that is our VOD, the differential output, which is called VC2 minus VC1, and that is our differential output. And the VC2 and VC1 taken from a single node, we call it single-ended output. So this is how we can take the output in different ways. And then we have the current source. So these two transistors, they are biased by the current source. This current will split between Q1 and Q2 and provide the bias current. So we can, let's say, denote the current that is flowing here as emitter current IE1, and the current that is flowing here we can show it emitter current IE2, right? Then the current that will flow here, that will be IC1, and current that will flow here is IC2. So differential amplifier, purpose of the differential amplifier is to amplify the difference between the two input signals. Right? So there are two inputs, and the output should be proportional to the difference between the two input signals. So that's the purpose of what we call the differential amplifier. Right? So we'll have the differential input signal here, the VID, which is the difference between these two, VB1 and VB2, and that is called the differential input, right? Differential input voltage. And so the gain of this amplifier we can denote as the differential gain, which we can define in different ways. We can also define like VOD minus VID. So that is our differential gain for differential output. Right? So output is taken differentially between the two output nodes. So there's a differential gain with differential output. Or you can take output just from a single node collector, let's say VC1 by VID. Okay? Or you can take from collector to VC2, then VC2 by VID. Either way, I mean, you can take the output and then gain will be defined like this. And there's also differential gain because the input is a differential input voltage. So differential gain for, then we call it single-ended output. The differential gain for single-ended output. We are taking output from a single node. Now, circuit at the first sight might look complicated. So in order to understand how the circuit operates, to get an insight into the circuit operation, so first we try to analyze the circuit for DC voltage and current, and then we'll analyze the circuit for small signal voltage and current. So DC voltage and current, that we call the large signal. Okay? How does the circuit operates for? large signal. So in the large signal, the voltage and current, they are usually in the range of, okay, large signal, let's forget about the current. The voltage will be in the range of volt, right? Or, yeah, or hundreds of millivolts. So that's our large signal operation. And the small signal, what is our small signal?
So 10 millivolt.
What is 10 millivolt?
Sir.
What is 10 millivolt?
So 10 millivolts.
Yeah, what is 10 millivolt? Which voltage? See that usually when we talk about the small signal voltage, we mean this voltage between the this voltage, right? Let's call it a small signal VBE. So we mean this voltage, base to emitter voltage, right? So a small signal voltage means that this voltage VBE, base to emitter, should be less than or equal to 10 millivolt. Okay? So that is a small signal. So in this case, the input is VID. VID is the difference between these two. So in this case, VID, which is about 2 VBE, because from this point to this point, right? And that will be, should be less than or equal to 20 millivolt. So that will be, then we can call it a small signal voltage. Any question, guys?
Sir, which one is VID?
VID. VID is shown here, VB1 minus VB2.
Okay.
Okay. Okay, so for both large signals, so first we'll focus on the large signal operation. Right? Easy to understand the large signal operation. So we can have two different mode of operation in both large signal and small signal operation. They are called the common mode operation and differential mode operation. If the two voltages are same, let's say VB1 is same as VB2, right? If these two voltages are same, then we call this common mode operation. And if they are not same, VB1 is not same as VB2, then we call it differential mode operation. So first we'll see how does it operate in common mode operation and when the two input voltages are same. So these two are same, assuming these two same. Okay. So these two same means, let's say we call it VCM, right? The VCM is called the common mode. CM stands for common mode voltage. And that also we can show like this. Uh, if these two are same, that means you are applying the same voltage, right? You join these two, right? And applying a common voltage here, which is called VCM. Right? So the same voltage VB1 and VB2 is same as VCM. So this is how we achieve the common mode operation. Now what happens in common mode? And this is our large signal operation. So VCM supposedly in the range of volts, uh, large enough to forward bias these junctions, uh, to forward bias these base emitter junctions. So what we'll have here that, so we have a forward bias voltage drop here, VB, and also a forward bias voltage drop VB. So let's learn this for VB1 and this one VB2. Now, since they are tied together, the bases are tied together, we assume these two transistors are, I mean, they are same, exactly same. They have everything same. Their dimensions and all the features are same. They are identical. Then we expect that VB1 will be same as VB2. These two voltages, forward bias voltages will be, of course, they are tied together, so they have to be same. Sorry. So these two are same. And so if these two are same, now we have a common voltage here. This is a common node. So we have a common voltage here at this node, and the voltage, what will the voltage here? So this is the emitter point, right? So we can call it VE, right? Voltage at the emitter. So how much will be this voltage at the emitter? Yes, difficult question. Well, circuit one question.
Sir, zero.
Why zero? It's not connected to ground, that is zero.
So then VBE plus VCM, VBE.
VBE plus VCM. That difficult. Voltage at this end is VCM, right? Then you have a drop of VBE. Then what do we get?
VCM minus VBE2.
Right, that is VCM minus VBE. That's pretty straightforward, no? Voltage here is VCM. Then you have a drop of VBE, so VCM minus VBE is the voltage at this point. Yeah. So that is V. Now you see that both the transistors we have assumed they're identical and they have the same VBE, right? For both the transistors. So what will happen since they have the same bias for bias voltage? This current I will divide equally between these two Q1 and Q2. So what will have that IE1 will be same as IE2. And these two will be same since they have the same forward bias voltage, and that will be half of this current. Right? Since the summation of these two will be I. So IE1 and IE2 will be I, half of I, and IC1 is alpha IE1, right? IC2 is alpha IE2, right? So what we can see that IC1 is equal to IC2, and that will be equal to alpha I by 2. So we got the expression for the currents, right? IC1 and IC2. So now you can also calculate the voltages. So we can calculate the voltages of VC1. VC1 will be this voltage VCC minus IC1 RC, and VC2 will be VCC minus IC2 RC. And IC1 we have already determined, so that is alpha I by 2. So this is alpha I by 2 RC, and this is also same VCC minus alpha I by 2 RC. So VC1 and VC2 they are same, and this is the output voltage from a single node, and VOD, the differential output voltage, is given as VC2 minus VC1, and since these two are same, the differential output voltage is 0. So this is the common mode operation, how the circuit will behave, what will be the current and voltages at the different nodes. VC1 the same as VC2, right? And we have the voltage at each of these nodes, but differential output voltage is 0 since both these voltages are same. Any question, guys? Is it understood? It's understood, right?
Yes, sir. Sir, are we also considering the DC voltages with the AC ones?
No, it's just the DC, right? There's no AC here.
Okay.
Mm. DC and they are large, right? Large enough to fraud by this base emitter voltage, right? Base emitter junction. VB is at least 0.7, right? So VCM has to be greater than 0.7 at least, or at least 0.7. So that is a large signal voltage. 0.7 means 700 millivolt. Okay? The small signal means only 20 millivolt. So now we consider the differential mode operation. And the differential mode operation, these two are not same. VB1 is not same as VB2, and that is called differential mode operation. And in this case, so there will be a differential input voltage since these two are not same, and that we can express VID as VB1 minus VB2, right? And so this is, we call it, so that is our differential input voltage. So in this case, since see that a signal is large, what happens now? So this is large enough to be, okay, I have to change the circuit here because we don't have a common voltage anymore. So we have a voltage VB1 and voltage VB2. These two voltages are different and their emitters are tied together. So we have a common voltage here, VE. And so these two voltages will be different, VB1 and VB2. These two will be different because VB1 and VB2 are not same, right? Now VB1 we can express like this. VB1 we can write as VBE. Okay, it's not necessary. Just write VB1. VB1 we can VBE1 we can write as VBE. VBE plus VID by 2, and VBE2 we can write as VBE minus VID by 2. Okay. So assuming that VB1 is greater than VB2, this voltage here is greater than this voltage. So the voltage VB1 will be greater than voltage VB2. Right? So, and then we can express this as VB plus VID by 2, VB this one VB2 minus VID by 2. And if you take the difference here, the two difference between the two voltage difference will be VID, which is actually the difference between these two terminals. Right? So we have the same difference remains same, half of VID here and then other half here. So the total voltage difference remains same. So this is how the voltage will be distributed. And you might ask why the half will be here and the other half will be kind of different distribution. Yeah, we can have different distribution, but since we assume that these two transistors are identical, right? I mean, they have exactly same parameters for everything. So it is, I mean, the voltage will only divide equally. If you have two equal resistors, right? So the voltage will divide equally. So if you have different resistors, then the voltage will have different, I mean, distribution of the voltages. But here in this case, we have assumed the two transistors to be identical, so they will have same the base emitter resistance, right? And the VID, the differential voltage, is also divided equally between these two transistors. So this is how we can have the voltage distribution, the base emitter voltage. So we have a slightly higher voltage drop, higher forward bias voltage for Q1, and slightly lower base forward bias voltage for Q2. Is that clear, guys? Any question? Now, what will be the effect of this higher forward bias voltage? Previous case, when we had the common voltage for the two nodes, then we had the same base two emitter voltages, same forward bias voltage, and in that situation, the IE1 was equal to IE2, and that was I. So let's write this on here. So the just as a reference. So in the common mode case, we had IE1 is equal to IE2, and that was equal to I by 2, right? So that was in common mode situation when VB1 was equal to VB2, right? And that was equal to VCM, right? Common mode situation. We had the two base emitter voltages. VB1 was equal to VB2, right? And VBE. So this current divided equally. Now, what happened in this case? VB1 has increased and VB2 has decreased by the same amount. So what will happen? That current IE1, this will increase, and this will go up, and while IE2 will decrease, it will go down. But they will increase and decrease by the same amount, right? Because the forward bias voltage has increased and decreased by the similar amount. So we'll have the similar, I mean, increase and decrease in the that will be reflected in the increase and decrease of the bias currents IE1. So now we can write that the IE1 we can write as, let's say, before it was I by 2, now we can write as del I. So the forward bias current will increase by amount of del I for IE1, and forward bias current for IE2 will decrease by the amount del I minus del I. Guys, that part clear? While the forward bias voltage increases by this amount VID by 2, the forward bias, the bias current increases by the small some amount in there, so we denote as del I. And this forward bias voltage decreases by VID by 2, and this bias current decreases by the amount del I. You see that when you add these two up, I1 and I2, so you get the same current, I1 plus I2, right? Total current should be I, right? So that is our bus current here. I is constant current source, right? Is supplying this. So the total current summation of these two must be I, and that is still maintained, right? Any question, guys?
No, sir.
Okay, now that we have determined I1, I2, so now we can write that IC1 will be alpha I1 and IC2 will be alpha I2. And then we can also write the expressions for the voltages. Okay, so the two collector voltages, VC1, we can write as VCC, that minus IC1 RC, and VC2, which is VCC minus IC2 RC. Right? Then IC1 we have written here as an alpha IE1. That is VCC minus IC1. IC1 is alpha. We have alpha, and then we have IE1. IE1, this is our IE1. Just directly write this one. That is I by 2 plus del I, and that times RC. So that is our alpha IE1 RC. And for VC2, we write similarly VCC minus alpha. In this case, IE2 is I by 2 minus alpha minus del I. So I by 2 minus del I times RC. So these are the expressions for the collector voltages, and from this we can write the expression for the differential output voltage DOD, which will be VC2 minus VC1. If you take the difference, see that VC and VC will cancel out, and I by 2, this is same, sign, this 2 will be also cancelled out, and we will be left with only del I and here minus del I. So these two will add up, and so VC2 is positive, and this becomes positive. We'll have 2 alpha del I RC. So that will be our differential output voltage. Any question, guys?
No, sir. Sir, we have increased VBE1 by VID by 2 and also decreased VB2 by the same amount.
Yeah,
Sir, can there be any situations where these increase and decrease factors are different?
I have already explained that. You notice that I said that we have assumed that these two transistors, Q1 and Q2, are identical.
Okay.
Identical, what does it mean? They are everything same. And among those, everything also includes let's say what counts here is the base emitter resistance. Right? The R pi will be same for both the cases. So if you have the equal amount of resistance, right? Then what do you expect? If you draw it like this, you have R pi and also R pi, right? So this your the end where you're applying VB1, and this is the end where you're applying VB2. And this is the common emitter terminal, right? This is the common emitter terminal. You have R pi and R pi. So what do you expect? How the voltage should divide?
Yes, sir. Equally.
Equally, right? As long as these two are identical, this voltage will divide equally, right? If you had, I mean, non-identical transistors, different dimensions, different resistance, then it will divide unequally, right? The distribution will not be even. Is that clear?
Yes, sir.
Okay. So that is large signal operation. And from this large signal, now we go for a small signal. Now, a small signal here, the condition for a small signal operation is that VID, not VB, right? VB1 has to be large enough to forward bias the base emitter junction. Or if VB1 is not large, if this is small, then there will be some other mechanism to forward bias the base emitter junction. This can be small as well. Now, as long as this can be forward biased by either this current source here or either by the supply voltage there, right? So that can be done by the current source here as well. But this can be large or small. But what is more important for the small signal operation, that the differential input voltage VID has to be small, right? VID, which is the difference between VB1 and VB2. This has to be small, right? Than 20 millivolt. That's the condition. So others you can have large values. So that is our present is a small signal operation. For a small signal operation, if you want to analyze the circuit for a small signal, what do you do first? What is the first thing we do for a small signal operation?
Or equivalent circuits. Remove these voltages.
Before drawing the equivalent circuit, what is the thing we do? You set the DC voltages and current to zero, right? The DC voltage, supply voltage VCC will be zero. The supply current I will be zero, right? You set these voltages and currents to zero before you analyze the circuit for small signals. Is that correct?
Yes, sir.
So if you do that, then what happens? This gets connected to ground, right? And you will not have this. But this will not work now. And VB1, the bias voltage, since we have removed the bias voltage, so the bias voltage VB will be also set to 0. And VB1, before we had written this as VB plus VID by 2, and VB2, we have written VB minus VID by 2. For the small signal now, when you set this DC voltage and current to 0, so that means that we have to remove also this DC part of the bias voltage, right? And we keep only the AC part, that is VID by 2 and minus VID by 2 for the voltage between base and emitter. So that doesn't mean that we do not have the DC voltage, the bias. We have the bias voltage, but we are not including this in our circuit because we are analyzing the circuit for small signals, and the DC bias voltage and current is there in the real circuit, because without the DC bias voltage and current, the circuit will not work, right? But we are carrying out the analysis for the small signal, and we have to consider only the small signal, setting all the DC, the large signal voltage and current to 0. Is that clear?
Yes, sir.
Question, guys? On this one. So in that case, if you draw this circuit, it will look like this. Now we have set VCC to 0. That means this effectively they are connected to ground. This voltage is 0. Then you have here VB1, and here you have VB2. And then this I is 0, right? So this open circuit here, right? So we have removed the current source, circuit is open, I is 0. Now VB1 minus VB2 is our the input voltage VID, differential input voltage. So that we can show like this if you just extend from here. So that is our VID to VID plus on this side minus on this side. This is Q1 and Q2. You have, this is our VC1 and VC2. And that is our differential output voltage, VOD. Now, this VID will divide, as I said, for identical transistor, divide equally between Q1 and Q2. So you have VID by 2, plus on this side, minus on this side. And then other half of VID plus on this side minus on this side. So the total you see remains VID, right? Half VID plus half VID is a VID. So the difference between V1 minus V2, VID. Is that clear, guys?
Yes, sir.
Yeah. So you see that when you have this voltage here VID by 2, then the current here is IC1 and current here is IC2. These are all small signal currents, right? Here is writing in these small letters. So how much will be IC1?
So VC1 by RC.
No, that is not correct. That is, I mean, that is not wrong, but that's not what we are looking for.
Sir, GM VID by 2.
Right, IC is GMVB, so we can write IC in this case is GM, VB is VID by 2. Okay? And similarly, IC2, in this case, it will be GM. Now, VID in this case, we have negative, right? So it will be minus GM VID by 2. VB is minus, in this case, VB, the base emitter voltage for Q2 is minus VID by 2. Right? So basically what is happening, actually this current is flowing actually upward, right? The positive direction of current is upward. Showing negative means it's actually flowing upward. So if we change the direction here, maybe that will be easy for us to understand. So let's remove this one. And upward. So it's actually flowing in the opposite direction because voltage here is negative. So once you have once you know the currents, you can also now determine the voltages. The VC1. What will be VC1 now? Come on, it's very simple, right? I mean, just need to find the voltage. That's complicated.
IC1 RC.
IC1 RC, but with a minus sign. The current is going upward. It will be minus IC1 RC1, and then you have IC1 is GM VID by 2. You have minus GM VID by 2 divided by RC, and VC2 will be IC to RC. In this case, it will be plus because current is flowing down, right? So, and we have GM VID by 2 RC. And then if you take the difference between these two, you get the differential output voltage, which is VC2 minus VC1, and then that will be GM VID RC. Right? So these two are, we call it single-ended. single-ended output voltage, and this is our differential output voltage. So once you have determined the voltages, you can now determine the differential gain, which is differential output or single-ended. Start with the single-ended, or yeah, VC1 by VIT. So that's the first expression here, VC1 by VIT, and that will be minus half GMRC. And then we can have VC2 by VIT, that will be plus half GMRC. And then we can have differential output VOD by VIT, and that will be GMRC. Okay. So these are the gains for single-ended output, and that is the gain for differential output. So the single-ended output voltage or differential output voltage is twice the single-ended output voltages, and the gain for differential output is also twice the gain for the single-ended output voltages. And single-ended output voltage, the VC1 is negative and VC2 is positive, right? So for gain also VC2 for gain is positive, for VC1 gain is negative. Any question, guys?
No, sir.
Okay, time is already up, so that will be all for today. And see you next class.
Okay. Assalamu alaikum, sir.
Wa alaikum assalam.